This video is about intermolecular bonding. And by that I mean the bonding between molecules. So I'm not really talking about covalent bonding or ionic bonding here. I'm talking about something else, though it's related. Let's look at CO2. Now, this carbon-oxygen bond in this molecule is actually a polar bond, but because there's two of them, they cancel each other out, and the whole molecule is nonpolar. There is no net charge on one side or the other of this molecule. So if you think about that, why would one molecule of CO2 ever be attracted to another molecule of CO2? And the answer is, well, they're not very attracted. That's one of the reasons CO2 is a gas under very low temperatures. The sign of not very much attraction between things is it's a gas under normal conditions. That's called having a low melting point, a low boiling point. But there is some attraction here. And this attraction is called London dispersion forces. Now remember, we're not talking about bonds between this carbon atom and this oxygen atom. That's not what we're talking about. What we're talking about is an attraction between these two different molecules. Now, think about this CO2 molecule. Essentially, we've got an electron cloud around the outside. And electrons move around randomly. So at some point in this random motion, there's going to be what's called a temporary dipole. That is, sometime in this random motion, there's going to be a kind of partial negative end to this molecule and a kind of partial positive end to this molecule. Now, these are not permanent. These are temporary. They disappear almost as fast as they appear. But for that moment they exist, causes like a chain reaction. Think about doing the wave in a football stadium. The negative here, this partial negative, has an effect on this adjacent electron cloud. Kind of pushes the electrons away from it. So just for a moment, there's a partial positive here and a partial negative here. And that's what's causing this very weak attraction between the molecules. This idea of these temporary dipoles. Dipole meaning one end is positive and one end is negative. Di means two, pole, like the North Pole and the South Pole. But very temporary, not permanent, and that's why these are weak. Very, very weak bonds. And this happens between nonpolar molecules. Now, what about molecules that are not nonpolar? Molecules that are polar. This is NO2. NO2 is a polar molecule. Not only do the NO bonds polar, but the molecule is not symmetrical. So there's this partial negative end here and this partial positive end here, but they're permanent dipoles. Permanent dipoles, not the temporary dipoles of the nonpolar covalent molecules. These are permanent dipoles. There is always a sort of kind of partial positive end to this molecule and a sort of kind of negative end to this molecule. Notice I'm not using real charges. I'm using these delta here, this partial charge thing, because this is still covalently bonded. Now this molecule here has the same partial negative and partial positive. So this guy with its partial negative would attract me to this guy. So I'm going to move this. So the partial positive end of this molecule will be attracted to the partial negative end of this molecule. And remember, we're talking about lots and lots of molecules, not just one or two, right? Think about a mole. This is called dipole bonding. Now, there's actually a special case of dipole, and that's when you have something like water. It's hydrogen on one molecule and an N, an O, or an F on another molecule. It's just a very strong dipole. So again, this guy is partial negative, this end is partial positive, this end is partial negative, this end is partial positive. So there's an attraction between the partial negative end of one molecule and the partial positive end of the other molecule. But because H is so small and N, O, and F are so very electronegative, this is a very strong bond. This is why water boils at 100 degrees Celsius. It's a much higher boiling point than, say, H2S, which would be the same thing. And you look at these and you think, wow, H2S, H2O, those should practically be the same. S and O are very near each other on the periodic table. But S is not nearly as electronegative as oxygen. So while this bonding, intermolecular bonding, between H2S is simply dipole, between the water it's called hydrogen bonding. And that's just a very strong form of dipole. And it's characterized by very high boiling points because it takes a lot to break this bond. Remember, when you're boiling water, you're not breaking the bond between the atoms, you're breaking bonds between the molecules. But it's that bond that's unusually strong, and that's why water has a very high boiling point. Now, be careful, because hydrogen bonding really does have a very specific definition. It's a bond between hydrogen on one molecule and an N, an O, or an F on another molecule. Sometimes people think anytime hydrogen is around, it's always a hydrogen bond. But that's not true. It's this very specific definition. Okay, so when we're talking about intermolecular bonding, we're either talking about London dispersion or dipole, or hydrogen bonding. Those are the bonds between covalent molecules. The weakest of those is London, then comes dipole, then comes hydrogen bonding. All of those, however, are weak compared to ionic bonding. This is why covalent compounds have lower melting and boiling points than ionic compounds, because London dispersion, dipole, and hydrogen bonding are less strong than ionic bonding. When something boils, if I were to actually melt this salt into a liquid and try to boil it, that's an extremely high temperature, because I would have to break these electrostatic attractions between the ions. You'll notice there is not really any such thing as intermolecular bonding in ionic. I'm breaking those same electrostatic bonds we talked about in the last video. So ionic things, much higher melting and boiling points than covalent molecules.